Welcome to the TEEP podcast, brought to you by the State Energy Conservation Office in Austin, Texas, and UH Energy here in Houston, Texas. I'm your host, Gary Gildert. We bring you the latest in industrial energy efficiency in 15 minutes or so. This week, we bring you an interview with my friend Jim Risko, the steam system guru. He's also the instructor for the Risko Steam System Masterclass Workshop for Refinery and Chemical Plants. That will be held August the 20th and 21st at the University of Houston Technology Bridge. So, Jim, before we talk about the workshop, let's learn a little bit about you. So, first of all, how did you even get started in reviewing steam systems?
Thanks, Gary. That's a great question. It's really funny. I got started in steam systems by happenstance. A little discussed part of my career is actually I started in mining engineering. And I thought I was going to work in a mine, but I ultimately decided to get my first degree in mathematics. And I had a heavy background in computer programming during the infancy of the programming revolution. So I thought I was going to do that, but things happened within my family and decided to stay close to home to be near my mother and father to help them. And I took a job where I was working with steam systems. The senior engineers there were very talented. They were like Virginia Tech and Lehigh University grads and Drexel University grads. But they were seniors and they didn't want to travel. So it turned out that there were a lot of steam questions that came up all over the country and they didn't want to travel. So they said, like, Jim, would you want to go? Oh, sure. You haven't lived until you've been 12 foot off of a ladder taking apart a 6-inch valve or something, you know.
Yeah. So you've seen a lot of systems, I take it.
I've seen a lot of systems. So what actually happened is I like to volunteer for solid over 2 years. I was out every chance I could all over. And originally it was places like Jolly Green Giant plants and chocolate plants and things like that. But then it got into refineries and chemical plants, a lot down, like down in the Gulf Coast, you know, Baton Rouge, New Orleans, certainly Texas, a lot in the Midwest, you know, with different refiners there, whether it was Salt Lake or in, you know, Oklahoma, and then the Midwest up in Chicago and stuff like that. And I just got to more and more questions would come up and more people kept asking me to solve those questions. And I may not be the most brilliant guy in the world, but I've seen a lot of applications and there, a lot of times they're similar.
Yeah. And this is the comment I would make is like, okay, so I started my career in plant operations and I've visited dozens and dozens of plants. To be honest, the steam systems all look the same. So aren't you just answering the same question over and over again? Like what's the difference?
You know, that's really a great question. Are the steam systems the same? Yes and no. They all look the same because the steam's contained in the pipe.
Yeah, well, those are the basics. That's where they should be.
But the fact of the matter is, I think that chemical engineers and mechanical engineers, predominantly in these types of systems, they don't get a lot of training on steam. They get a couple of days maybe in thermodynamics. But the fact of the matter is, it's pervasive throughout plants that people refer to steam as saturated steam. Yeah. And to me, subconsciously, that builds a false sense of security in their mind. Because the fact of the matter is, none of their steam is saturated. All of their steam is either superheated, and then it crosses over the saturation threshold and becomes wet steam. And the quality of wetness, so I know originally you're from Canada, they carry slurries of an oil sand that could have 30% wetness in the steam.
Yeah.
And it's common in the United States and Canada in regular plants, other than, you know, SAGD plants or anything like that. It's common in plants to have 10, 15% of wetness in the steam. The more wetness have, the more it can negatively affect operations. And then people do non-energy saving things like open bypass valves, open bleeds to the atmosphere. And then ultimately they get a lot of venting out of systems because they're doing some crazy things. So the steam is not the same, and every plant's unique.
Yeah, I'm used. Maybe I worked more on newer systems where it was all nice, superheated steam just about everywhere except for the neglected parts of the plant. I guess that's where some of the business would come from.
Well, I mean, no, the superheated steam is used in plants that would do that to drive turbines or where they need high temperature operations, but predominantly that stuff is desuperheated and you don't get the conductivity of superheated steam is extremely poor because it's a dry gas. So when you're talking about heat transfer, which is happening in predominant amount of applications, you need to have saturated steam, which you don't have because that's the threshold. So what you do have is wet steam, and that amount of wetness can affect different operations. So that's what I tend to deal with a lot. You would be surprised, but so many of the issues, whether you have a mile line of resid that solidified because they didn't trap it properly, or when you take a look that they're pulling out sections of sulfur piping because it's solidified and frozen.
Yeah, that's a good reminder. There were desuperheating stations around upstream of the heavy-duty heat exchanger systems. So you're right. Yeah, and all the all of the steam turbines, they required superheated steam in order to work well without getting erosion. So yeah, you're right. There is a lot of complexity in there that we just don't learn as in undergraduate programs normally. So,
and you learn it in the plant. So you mentioned desuperheaters. Okay, so desuperheaters, for example, are normally way out of the area that you can't see. And then the way they're designed is people don't know when those desuperheating valves have gone bad and they're blowing a lot of water into the system, too much water. And you think that, okay, it's blowing condensate into the system, but I'm going to catch that with the way I'm maintaining the superheat, Jim, at like 15 degrees Fahrenheit above saturation level. But you don't see the river of water running along the bottom of the pipe.
Yeah, it takes some incredible instrumentation to make sure that you haven't crossed over the line from a little bit of superheat to wetness. And you're right, you cannot tell degree of wetness just from standard instrumentation.
But believe it or not, Gary, I know you're ready to ask me another question, but I'm going to say to you that I have a very simple method to determine if you crossed over that threshold.
So the next thing I want to ask you about is in terms of plant operations. Do you think operators normally look at their steam systems and their maintenance? Is this a reliability thing, or are they working on energy efficiency?
My sole purpose is to work on safe manufacturing practice.
Yeah.
It's really up to the design of the plant and other personnel, whether it's maintenance crew or energy team. It's really up to them to optimize the use of energy. So as an operator, my job is to make the manufacturing throughput that I need. So if that means a reboiler or a heat exchanger isn't working properly and it's not draining condensate, for example, I better throw open that bypass valve to make sure that I get what I want out of it. But then they don't stay there and maintain it. So now you can have a bypass valve. We had one instance that I talk about that's 28,000 pounds an hour of steam was blowing into the return header. So when you think about, so first of all, they lost a duty from the manufacturing process, okay? Because you can't have that much steam going through that into the return header. But if you follow that all the way down to the flash drum and you take a look at what's being vented, it may not be 28,000 pounds, but if it's 15,000 pounds, what they've got is $500,000 a year energy loss and all the emissions that go with it. So if you can track that back and reduce the firing of the boiler, then you have a big energy benefit. And that's what, I know that early, I'm going to call you Dr. Gary. Early in your career, I know you did steam balance. So you understand exactly what I'm saying. No energy benefit is worth it unless you can reduce what's happening with the boiler. So we have to track it back through the steam balance to the boiler and make sure that all these applications are working that way. So operators, to get back to your question, operators have to focus on production, and it's really up to the plant design to make sure that they're using the least amount of energy to accomplish their production goals, and that goes directly to the EII or the EEI, depending on whether you're a refinery chemical plant. And that determines what quadrants they fall into in terms of effectiveness of their manufacturing.
So you've worked a lot with steam traps and condensate pumps in your career. Is this really the main problems with steam systems?
I think the main problem with steam systems, this is a great question. I think the main problems with steam systems is people want to have an optimized steam system. You can't go to somebody and say, Gary, would you prefer to have suboptimal production? Would you prefer to do your manufacturing with suboptimal heat asset? But people don't know how to do it. So the extent that steam trapping comes in to maintain, and separation comes in to maintain the quality of the steam. And pumping comes in to return condensate back to where it can be used at a DA. What I try to have people understand the entire steam condensate loop, is like we had one application in a Gulf Coast refinery that was wasting 18 million gallons of condensate in a drought-stricken area a year from one reboiler.
Ouch.
But that was just for them a cost of production because they didn't know how to fix it. So that was a simple solution how to fix it, okay? After I analyzed it, myself and my team. But 18 million gallons, think about that, and all the energy loss. So then what happens is you're not returning that high temperature and treated water back to the boiler. So now you've got to divert your plant steam and use that for the makeup water that's going to go into the boiler to heat the makeup water. So now when you have rainy days, you might lose a PSI or two off of your steam header, and that can relate to a couple of degrees temperature, which is going to affect your temperature drive to manufacturing. So the energy component all fits into the manufacturing component and vice versa.
It does sound like reliability and energy efficiency really do go hand in hand. And what I'm looking forward to is you showing me how we can achieve both on there. So this is our segue to you telling me a little bit more about the master class that you're going to be teaching. Tell me more about it. And why do you call it a master class? Isn't it good for everyone?
No, it's actually not good for everyone, believe it or not. So people, when they think about steam systems and talking to someone who worked for 48 years with steam traps and pumps and valves, think, oh, this guy's going to talk to me about steam traps and pumps. Not really. You should take the site will have a preferred or historical vendor and go attend their steam trap and pumping and valve class to learn how those items function. That is not at all what this is about. You can have a variety of companies do that. So when I would go and analyze different problems around the United States or the world in some cases, whether it's a turbine in Italy or something like that, or something going on in Australia or Japan, Singapore, a lot of the problems repeated. So if you're an engineer on a job in a plant, you might be in that job for, 3 years and off to another role. So you might see one of these events, but then you're off to another role. Now, the operators will see them commonly a lot because they'll tend to stay in that position more, but the engineers don't. So, you get that kind of satisfice and you move on to your next role, and it's the next engineer's problem and the next engineer's problem. I remember a paraxylene chute that they had it fixed 2 times and it didn't work right. They were getting like 800 blocks a year on the paraxylene chute, okay? And a simple solution fixed it, right? And I'm going to talk about that. So, the problem with it is you have to understand the systems. So what I did is over time is when I would see an interesting thing that I thought people should know about, I wrote an article about it. And I have like various places, over 80 articles, but what I did is I took 24 articles.
Okay.
And those 24 articles, which were all of them were in chemical engineering, hydrocarbon processing, or AICHE's chemical engineering progress. And they were all the feature stories. And that's the background of the modules that I decided to use. It's the typical applications. You need to know about water hammer issues and steam quality, condensate water hammer, okay? You need to know about turbines, flares, steam heated storage tanks, steam assisted flares, and things, steam-driven turbines.
Yeah, I was going to ask you about, because I attended your workshop last year, and you've got some just amazing graphics and just amazing stories that you tell about this. So this is all derived from the articles you've written.
Well, yes, but in all fairness, the articles are driven from case histories.
Okay.
So what would happen is when I was president of the company where I worked, I developed something called zero installation defects. It's one thing to buy a product, but if you don't know how to install it, you can still have a defect. I didn't want to call that acronym ZID, zero, because it sounds kind of funny. So we called it the ZD manual. And all of the engineers were required to follow proven practices. So whenever we would look at a heat exchanger or reboiler or flare system, some problem here, some problem there, some problem with tracing system, whatever, we would follow the proven practice that would work and give that recommendation.
Okay.
And, we never would go to somebody and say, do this application unless it was proven. And if it wasn't already proven, about 8 of us would sit together, come up with what we thought would be a solution, and tell the client that it was an experimental solution that we think is going to work, but we can't guarantee it because we haven't done it before. We actually never had an experimental situation not work.
Okay. That's a little bit of luck and skill.
No, because we analyzed them.
Okay.
I was never throughout my career in the process of playing Russian roulette with somebody's job.
Yeah.
Okay. And the safety of a site. What I write, I'm mostly retired now, except for my work with TEEP and things like that, and solving, kind of specialized issues. But this is all about helping people say, look, these are the sites, these are the problems. Nobody ever called me into a site and said, Jim, come here. I want to show you how beautiful my site's working.
No, it wasn't always a picnic.
And the funny thing about it is I remember, just tell you 2 quick instances. Okay. One site was having an issue. It's in let's say the Gulf Coast area around Texas. Okay.
Yeah. We don't want to name names.
No, I'm not going to name names, but they were having an issue with, they had condensate pouring out of a vent and it was spilling hot condensate on people. So they analyzed it for 6 months, and they actually had an EPC firm look at it for 3 months, and they couldn't solve the issue. So when I'm talking with my team about it, I'm taking a look at it, and 20 minutes later, after we're looking at the P&IDs, we're like, yeah, this is the problem right here, and that was the problem. So I had another case a little further east, okay? And I remember they were having a problem with a reboiler, and they had spent $1.8 million to revamp it, and it still wasn't working right. I'm looking at the reboiler for 5 minutes, and I say to my guy, we better talk about the local football team, because if we go in after 5 minutes and tell them we figured out the problem, they're going to be upset. So is it because everybody's so smart? No. But when you see a problem happen 100 times, you know how to fix it, and that's what I publish. So those articles are, and you have them on the links. It's recommended reading if you want to attend the master class, because when you're doing an article, you can only sometimes put 8, 10 graphics. I think some of them I have 22 graphics. My latest, actually 25 on hydrocarbon processing was 25. This latest one in hard carbon processing that's coming up September, October has 22 graphics.
Wow.
So when you do that, it's to help people, but I can only do 22 graphics or 10 graphics. In the master class, I'm giving a lot more graphics in much greater detail. I'm not expecting anyone to understand everything in the master class, but they will have those articles that will jog their memory. So if they read the article, when you were in school, when I was in university, especially in mathematics, I always read ahead before I went to class, so that when I appeared in class, it was the second time I would see it.
Yeah.
If you read the articles, as many of the 24 as you can, and you come to the master class, you'll get a lot more out of it. And then those articles will serve as a constant refresher that you can always go back and refer to them. And that's what people have told me that have attended the master class. They refer to those articles commonly for the issues, whether it's on heat exchange or whatever.
Yeah, it's fantastic reference material. So who do you think should be going to this master class?
Well, I think that every university student that's an engineering student, in particular chemical and mechanical engineering, and in a lot of cases electrical engineering, because they're going to get involved with mechanical and chemical jobs if they're on a site.
Yeah.
I think throughout their career, they may go into a process side, or they may go become a project engineer or a process engineer, or they may be a maintenance engineer, they may be an energy engineer, and definitely the operators, because some plants, not all plants, but some plants, there's a disjoint between operators and engineers. The operators will see something, but they have the feeling that I can't tell the engineers because they're not going to do anything about it. And it's not all plants, because a lot of engineers are so smart, they want to hear from the operators, and they have a great relationship with the operators.
Absolutely.
So I think operators, they're on the site every day. They're out there working in that heat in a lot of cases, or the cold if it's up north. And I remember one site we walked onto, they were having problems with their 250-pound turbines. And we went to one of the trap locations that had moved the pipe 4 feet, from water hammer. And they had 7 traps. I think it was 6 or 7 traps down on the ground. They kept replacing the trap. They didn't realize it wasn't a trapping issue. It was a design issue.
Yeah. I hear what you're saying about operators, because I've always said, and I got along great with the operators in my plant, whether it was pilot plant or full-scale plants, is they are terrific observers. If you want to know what's really going on, listen to your operators. Now, interpretation, that could often be imaginative, but the observations are true, and that's what you go for. And it's our job as engineers to help them with that interpretation. And it's our job to assist them with that. So you think even undergraduates would get something out of this course?
I do, because they get a head start on it. I'll tell you one thing else.
Oh, yeah.
My daughter, she's an IP attorney now, but she is a chemical engineer, and she interned at a chemical site and a refinery site for 2 summers because she wanted to learn about that and MOCs and things like that. But she worked in a projects improvement team. And she told me that project improvements team had sometimes as many as 80 applications a year that needed revamps. So, a lot of times when I looked, and I worked a lot with design engineer groups over my life, so much with design engineering groups, okay, and process revamp groups, you name it.
Because you want them to get it right the first time.
You want them to get it right the first time, and certainly when they revamp it. But, a lot of times, I think nobody ever wants to do a bad job that's working for a site.
True.
But they have a certain amount of knowledge or a certain amount of time, and they don't have the time to do it properly, or they're doing what's been done before, which is why they're having the same problem. What was it they attribute to Einstein about doing something the same way and expecting a different result?
Yeah, that's the definition of insanity.
Yeah, so they have to take action of some sort, and then they get pulled off of it. So what I try to do is give them proven practices that work, and they've all been tested and tried and proven. So if they're applied properly and installed properly and maintained properly, this is a solution for them.
Okay. So we want to get even undergraduate engineers, certainly any engineer who's working in a plant, even if you call yourself the hydrocarbon processing engineer, you got to understand the utility systems, or else you'll just have problems. And folks in the EPC, let's learn from past problems, and we can use your experience to make for better designs. So there's a lot of different people who could benefit from this course. So the question comes up, okay, we're going to be in Houston, and it's live. There's no virtual. There's no option for hybrid or anything like that. We're not doing that, certainly this time. Do you give this masterclass in other places? I know at a much higher price, but that's another story.
Well, I actually have done that in the past. I've given the classes elsewhere, but right now, I'm pretty much United States and Canada.
Okay.
I mean, I could consider Europe, but it gets to be too far to travel, I'm sorry to say.
And there's no virtual option at this point.
I'm not doing virtual option because I don't want people to record the master class. In a sense, it's proprietary because it goes in deeper detail than what I've done in the articles. So, coming back to who should attend it, I will say one thing. I am firmly believing that no one can find any class like this anywhere.
Okay.
That will present this material based on case histories in this detail. So you said, should university students see it? Sure, because I don't know how long I'm going to keep doing this class. And these are problems that exist in refineries and chemical plants. So if you get a chance to see it now, it'll tuck away in your mind and your subconscious, and you'll have reference for it. And when you see it, you'll be the person on the spot that has possible solutions to optimize and correct the issue.
Absolutely. So, okay, we're going to wrap up here and just remind folks that the Risko Steam System Masterclass Workshop for refinery and chemical plants will be August the 20th and 21st at the University of Houston Technology Bridge. Registration details are going to be in the show notes and in the TEEP newsletter, or you can check out the UH Energy calendar, or just email me. Folks know how to get in touch with me now. So with that, thank you very much, Jim. It has been a pleasure. Most people don't know, but we were probably talking for half an hour before this because it's been so much fun, but we need to wrap up. So again, thank you, Jim, and we'll see everyone later.
Thank you very much, Gary, and to TEEP and the State of Texas Energy Conservation Office for sponsoring this. I hope to see everyone there.
Great. Thanks again.